continue what Karen was saying, most of our internal organs consist of tubes that are lined by a single layer of epithelial cells. Blood vessels she was talking about are lined by a modified type of epithelial cells called endothelial cells. These are some examples. And so what hasn't been noted before is that the branching patterns of tubes fall into two categories. The vast majority we'll call, and this is our terminology, R3 or R cube pattern, where the tips of the branches are dispersed roughly uniformly throughout the volume of the organ. And we call it R cubed or R3 because the volume is proportional to the radius cubed. And it's a very common pattern because the branches go throughout the entire volume. The tips, these are for, we're not talking about networks here, we're talking about branches that would end in blind-ended sacs. And this enables access to the whole organ. So if you want to have, deliver something or receive something from the entire volume of the organ, this is what you use. And the vast majority of organs, for example, the lung, the mammary gland, pancreas, salivary gland, and so forth, use this sort of pattern. But there is a different pattern, this hasn't been noted as far as we could tell, called the R squared or R2 pattern, where the tips of the branches all end near the surface of the organ. We call it R squared because the surface is proportional to the radius squared. And the main example is the kidney and the ureteric bud of the kidney. So Karen mentioned the kidney. The kidney actually has three different tubular networks in it, and only one of them, the ureteric bud, which becomes the collecting duct of the kidney, is the one that matters. Okay, so just to show you some examples from real life, these are stained images of developing systems. Over here is a developing lung taken by Ross Metzger, one of our collaborators, embryonic day 14. And you can see the tips are, this is a cross-section, so the tips are going in this cross-section through the entire volume. This is just a 2D slice through a three-dimensional structure. But if we look at the tips of the embryonic kidney, the tips all end at the surface in this cross-section. This is an R2, or if we take a surface view, the tips are ending at the surface. Okay. So no one's noticed this before as far as we can tell, and we tried to understand how these two different branching patterns are generated. Okay. And so we look at early kidney development, and this has been studied before. There's nothing new in the data, but there's something new in what we noticed. It was noticed by Wei Yu and Ross Metzger. So the earliest steps in budding, you start with a simple tube, and then it buds. It goes through 6 generations of budding, and they're all color-coded here. So this, in this brown, is the 6th bud. These are all, except for the very first one, these are all bifurcations. One splits into 2, okay? And they all initially happen at right angles. But the key point here is that at the 6th level, the 6th stage, if we look at this, and this is at 2 different orientations, turning 90 degrees, the what we call the child branch, these 2 here, is perpendicular to the parent, but it's parallel to the grandparent. So we have a relationship between the child and the grandparent. Okay, and you can see it here, they're parallel. It's not as, you can also see it here, but you have to rotate 90 degrees. I don't have a 3D viewing system for you here. Now, that's what gives you the R2. Now, in combination, R3 is a mixture, apparently random, 50-50 mixture, and I say apparently random because simply we haven't discerned what the pattern really is, of this parallel, this R2 pattern here, where it's parallel to the grandparent, child, and a different one, opposite, where it's perpendicular to the grandparent. See, here it's going in and out of the plane, and here, this is the grandparent. So it's perpendicular to the grandparent. Okay, the blue one is the grandparent. The, well, orange or brown, whatever you want to call it, is the parent. Excuse me, the child. So in kidney, starting with the 6th, the child is always perpendicular to the parent, but parallel to the grandparent. you get the R2. In lung, in many other organs, lung has been particularly studied by Ross Metzger, who was working with Wei-Yu to discover all this, you get this 50-50 mixture. So then we did in silico modeling, and this was all done by our chairman here, Wallace Marshall.
30 seconds.
And sorry.
30 seconds.
Oh, okay, so you can model it. Oops. You can model this, and this is a model of constructing the kidney pattern, and you can express this by whether you have the R2 or the R3 pattern at different stages, and you get, if you do that, this is the coding either R2 or R3 perpendicular parallel, you get different patterns here, and so Wallace did all possible combinations, and then he evaluated these by goodness of fit measures, including fractal dimensions and other things. You can read all about this. This was published in September in Cell Systems. Thank you.
Okay, next up we have Dr. Barbara Jones from IBM Almaden.
My collaborators are Grayson Lewis and Wallace Marshall, and I'm going to be talking about something rather different than the last few talks. I'm going to be talking about viruses in cells, and we model viruses as they first cross the gate and enter a cell. Once they're in the cell, they have to evade the immunity. The immunity reacts to them. If they successfully evade it, they're able to reproduce by using the structure of the cell, and then they escape, and in our model, they destroy the cell, and they mutate, and then the process continues. We have an interesting way of infection that models a little bit how the virus infects the cell. That is, that the cell is thought to have a gate of 50 amino acids, and in our model they can be from A through Z. The virus itself has 100, and the virus, when it approaches the cell, it rolls against this gate, and the alignment that has the maximal number of matches, we call the match number for that virus, and it turns out to be a key number in the model. So this is our simplified model. We have viruses in the environment. They enter the cell with a given match number to that cell, as I have just described. There they meet an immune response. The immune response has a functional dependence on whether it's seen the virus before. And then with a probability, again, based on its match number, the virus can reproduce, and when it reproduces among the 100 amino acids, one is allowed to mutate randomly, and that one that mutates, depending on whether it's in the matching alignment, it can either increase the number of matches, decrease, or keep the number of matches the same. This cohort, and then it's allowed, the fecundity we have is 20. So this cohort then goes back into the environment and then infects other cells. And this cycle continues. So they're the only equations in the entire talk, but it shows the probabilities for each of the three stages. Notably, we have a similar but not the same infection rate as the reproduction rate. The infection rate, the probability of any one attempt to enter a cell is an Arrhenius form, but it hops as it goes across the cells, and so it's slightly different. And what we find, which was published in 2015, is that this simple system has a first-order phase transition, a well-defined order parameter, which is the match number. And this is a plot of, as a function of temperature, which I haven't mentioned before, the Arrhenius form of the probability of a single entry and of reproduction is Arrhenius form e to the minus 50 minus the match number over the temperature. And then the immunity are the only two parameters that we vary in the problem. And then you see as we plot the batch number as a function of this phase space, we can get a first order phase transition. So this was published in 2015, and since then we've looked at this is the steady state, and we've now looked at the dynamics and asked the question, do the dynamics show any evidence of this phase transition to come in the dynamics that as the process proceeds of the various steps of this iteration of the viruses meeting cells, trying to infect, and if infecting, then mutating. And so modeling the time dependence, we've calculated actually many dynamical properties. Of course, in a short talk, I can only do a few of them, of the virus response and to the immunity and the response of the immunity in the cell. And here's one example. This is a plot of the response. First of all, every collection of viruses that we get naturally forms in this model a quasi-species, which is a more or less Gaussian distribution centered around an average match number. So if one looks at, for example, the various members of the quasi-species, which are the different colors in each plot, so each little subplot, the x-axis, is time, that is iteration number, and the y-axis is the growth rate. The different colors are the different components of the quasi-species. So you can see how the different components of the quasi-species differ in their growth rate, and they're showing different strategies of the viruses within the quasi-species to achieve equilibrium. And you can see that there are at least 3 distinct strategies for reaching equilibrium. We can also look at the how the viruses, and of course I should mention cells here because this is a conference on cells. In particular, this is a plot of in the environment, the viruses, and in the cells. The reddish on the top half of each plot are the viruses in the environment, and then the bottom half are the cells. And you can see that on either side of the phase transit, and then the x-axis is time. And you can see that there are 2 very distinct strategies that in one part of the phase diagram, the cells and the environment are very much alike. But in other parts of the phase diagram, they're exactly opposite. So that the strategy in one part of the phase diagram is such that the virus wants to increase the number in the environment, and this drains the number in the cells. Whereas in other parts of the strategy, the virus increases overall its population both in the environment and in the cells. So the summary, we have simulated the dynamics. We can model actually tens and thousands of cells and viruses on life-size scales of both time and distance. The viruses naturally form a quasi-species, and the phase transition broadly separates viruses of 2 types of strategies: those with a strong match, and those reproduce easily but are subject to immune predation, or those with very few matches, and they hide from the immunity, but once in the cell, they can survive. And we think of these as more, the one is influenza. It comes in with a bang. The immunity sees it eventually, but it survives by having a lot. Whereas chickenpox comes in and then hides, and then can show up 50 years later as shingles, right? So viruses can have very different strategies, and interestingly, this very simple model can show these 2 different strategies coming out. The dynamics clearly reflects the separation of behaviors, different strategies, and the extinction rate, which I haven't been able to show, has a strong dependence on initial infection patterns. And we welcome some ideas about how to use this model, for example, to change the immunity and also antivirals. Thank you very much.
All right, next up we have Lillian from the theory group at BioHub.
Oops. Hello, I'm Le from the theory group at CZ BioHub. Today I'm going to share a mystery about the luminar flow in the endoplastic reticulum, and it's well in complement with what Elena has just talked about. And so the ER network serves as a highway system that delivers functional particles or molecules inside our cells. And these particles are transported by the luminal flow in the ER tubular network. And this luminal flow has not been probed until very recently using single particle tracking method, where we have fluorescent particles that tracked inside the ER tubular network over time. So, and the velocity of the particles are measured, and which is assumed that captures the luminal flow. And interestingly, these particles are not doing simple thermal diffusion, which would then be captured by the velocity would then be captured by Maxwell-Boltzmann distribution that is shown by this white solid line, and the actual distribution is shown in the histogram, and which reveals an astonishing fact that the flow appears to be well quantized. You can clearly see the first peak around 5 to 6 micron per second, and the second peak at 11, and third peak at 17, and so on. You can count up to 6 peaks, and these peaks are separated by the same difference in terms of velocities. And so how can we understand this quantized distribution of velocity? But before we go into that direction, let me first try to answer why the luminal flows in the first place if they are not driven by thermal fluctuation. And here shows the endoplastic ER membrane that is resolved over time. You can see some tubules will contract every now and then, and that appears to drive the active luminal flow. As the lumen is approximately incompressible. And with that, we have already collected all the ingredients for a physical model. We have luminal flow that is constrained in the ER tubular network, which is a network of tubules that are connected with junctions. And these junctions are mostly 3 junctions. And second, we have some tubules will be active driven that induce flow, active flow in the network, and the lumen is incompressible, so that we will have a flow in the rest of the network. And based on these ingredients, we will then make a theoretical model. Just for simplicity, we will illustrate the model in the honeycomb lattice, where we have edges of the lattice edges that represents the tubules, and vertices represents the junctions. And in the honeycomb lattice, we'll have only 3 junctions, and we'll choose a fraction of edges to carry active flow, and which carries a single 1 unit of the flow. And then, because of this active flux and the conservation of the flow, there will be a passive flux in the rest of the network, so that the flux will add up to 0 at each junction. And then the problem becomes solving this passive flux X by giving some random set of active flux. And we are specifically interested in that when the fraction of active edges are given P, what it will be the distribution of the flux P of X. And well, that's sufficient to capture this quantized flux. And here shows the direct numerical test of the model. On the y-axis shows the density of the edge that carries given amount of flux. And we see a lot of edges that carries when the active edge is sparse, P is small. We see a lot of edges carries a very small amount of flux, and the density decays rapidly for large flux. And we see a single peak at flux equal to 1. But when we gradually increase this fraction P, we see the decay becomes flattened, and the higher quanta, the spikes at integer numbers becomes more and more populated. And when the fraction is about 1/3, we see a lot of edges that are even carrying the flux in 5 and 6 units. And that's very promising, and we can do some simple arithmetic of the flux to give some intuition on what's happening there. In the sparse case, when the P is very small, we can treat the active edges independently, and so the nearest neighbor of the active edge would carry 1/2 of the flux, and the next nearest 1/4, and 1/8 in the next nearest. So essentially, we have a lot more edges. When it's away from the active edge, we get more edges that carry smaller amount of flux. While in the other limit, when the active edges are very dense, we can see that the passive flux can actually add up in a quantized way. For example, here, when two edges merge at a vertex at a junction, the only flux conserving solution is to have the passive edge carry 2 units. And if it merges with another active edge, then it will carry 3 units, and so on. You can get all higher order integers. And there are a lot more interesting predictions of the model, and you're very welcome to catch me up to learn more about that. Thank you.
And so our last lightning talk of the morning is Ayelet Fusco from Hopkins Marine Station in Stanford.
So I will talk about a work that we did with Steve Quake and Erv Weissman in the last 5 years, and I will try to sum it in 5 minutes. How do I point with the red? No. Okay. So we are working on colonial tunicates, which are the closest invertebrate relative of chordate of vertebrate. And in the upper panel, we are looking, and they have 2 strategies for reproduction, sexual and asexual. Upper panel, regular sexual reproduction through embryogenesis, classical chordate embryogenesis. In the lower panel, they also reproduce through asexual reproduction pathway, through budding, stem cell, tissue-specific stem cells, homing to buds to niches of development, and through weekly cycles, they will reproduce the same adult body. And the question that we were asking is, how does these 2 different modes of reproduction are differ, how they are similar? We did it by using a RNA-seq. We took, and we can see it up on the left, we took key stages of development from the embryogenesis. We took key stages of development from the blastogenesis. And we also sequence tissues of the adult. Nervous system, the brain, the blood, hematopoietic stem cells, germline stem cells, etc. And now we can compare, on the molecular level, every stage of embryogenesis to itself, and this is what we can see in the heat map of the embryogenesis. Blastogenesis, every stage of development to itself and to all the rest on the other heat map. And then we can compare the stages of embryogenesis with the stages of blastogenesis. And what you can see is that they are very, very not similar. The highest correlation that we can get here is 0.3. With the tissue-specific signature that we can see in this heat map, we now could go back to this embryogenesis and blastogenesis pathway and follow the development of the organs. We combined it also, of course, with confocal imaging and electron microscopy imaging. And what we can see in this panel, the development of the brain and the nervous system in the embryos. In the bottom, the development of the brain in the through blastogenesis. And then in the 2 different graphs, we are looking on the enriched tissue-specific signature, and we can recognize when they originated through this development and their dynamic. And we did it also for other organs as well. And now we can look on the timing of when those organs evolve, compare it, of course, to the morphology. And we can see on the up is the embryogenesis pathway, on the bottom, the blastogenesis. The organs appear in the same order. And when we are looking on the, and what we see in the upper part, when we are looking on the tissue-specific signature of, in this case, the hematopoietic stem cells of this organism in the adult, we can see high signature of a specific gene set, and then the gene set that is coming on the after the organ is actually combined them. And then with the same set of genes, we are mimicking it or mirroring it to the embryogenesis, and we can see that they are actually acting the same. So this suggests to us that we are looking on, in this case, tissue-specific stem cells that when they evolve, they are actually similar between the two different pathways. And we were also compared it to other vertebrate, in this case to Amphioxus. And only when we were focusing on transcription factors, we actually could see some resemblance, again, to the relatively low. Again, the correlation here is 0.3, but these are the conserved. The summary we can skip because I actually told you everything, and I will just run to the acknowledgement. It was a big work. We just uploaded it to the bioRxiv. Thank you for listening.